Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. Now, if somebody asks you that how efficient, if somebody asks you that how efficient your recursive solution is, then we can answer them in these terms, right? For example, for this factorial function or power recursive, right? We can answer them in a specific term. So there is a formula that I'm going to tell you that is going to work for 70% of the cases, right? There are 30% of the recursive solutions where this formula will not work directly, although the essence of the formula is same, but the formula is not going to work directly, right? Till now, like whatever problems we are going to do in quite some time, most of them are going to be related to this formula, and we will be able to most probably evaluate things around it. So technically, if you want to calculate the time complexity of a function, then you need to calculate the number of instructions, right? Okay. Now in a recursive function, the number of instructions are not just of one function call. The number of instructions are going to come up from multiple function calls, because the same function call is calling itself. So the number of instructions is not just dependent on how many lines of code, or let's say how many actual instructions are executed in one function call. When you recursively call another function, then their number of instructions are also going to be added, right? For example, if I say here that I wanted to calculate a raised to the power b, I did only two instructions, that is to check whether b is 0 or not, and then multiplication. Apart from that, all of the instructions that were required to calculate a raised to the power b minus 1 will also be added. Now for a raised. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different. And a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. This one, you can say that to compute a raised per b minus 1, I did two operations. That is to check whether b minus 1 is 0 or not, and multiply a with whatever is the answer of a raised per b minus 2. So whatever is the number of instructions that is getting executed for a raised to the power b minus 2 will also be added in our answer, and so on, right? So this is how you will calculate the number of instructions, right? Because one function call is not just answerable for the number of instruction that is getting executed. The function call is actually going to call itself again and again with multiple parameters. So there are technically multiple function calls whose total instructions we have to aggregate. Okay. Now, how can you do it? If I just figure out the number of function calls, so if you see in a raised to the power b minus 1, the number of function calls is what? Let's say it is 2 raised per 3, then you call 2 raised per 2, then you call 2 raised per 1, then you call 2 raised per 0. This is one function call, second function call, third function call, fourth function call. So if the value was 3, there are 4 function calls. And the last one is technically a base case only, right? So we have, can I say that we have approximately b function calls, b plus 1 or b, when the value of b will be very high. It's approximately same, right? Okay. And if I calculate number of instructions in each call, for example, in one function call, what is happening? There is a constant operation of checking the if. This is a constant operation. Then there is a constant operation of multiplication and a constant operation of function call. Calling a function, like this step where I call a function. I'm not talking about how that function is computed or in the computation of the function, how much instructions are executed. I'm just calling the function. I'm just telling the system, hey, can you please go and start the function a raised per b minus 1? Can you just start that? So we are just triggering a function. Triggering a function is order of one task. It's a constant time task. So in one function call, constant time, multiplication is constant, triggering a function is constant. So in our case, can I say that one function call is technically of constant time, right? So using this formula, we can technically compute number of instructions. But again, I'm saying that this is going to work for 70% of the algorithms. For example, there are some algorithms which qualify themselves as divide and conquer algorithms. You will find a bit of difficulty using this there. So the method of computation is going to be a bit different. But for starters who have just started with recursion, this formula works fine. So if I try to figure out how many function calls are there for f of a comma b, there are approximately b function calls, approx. In each function call, you are doing constant time operation. This is the number of instruction. So if the number of instruction is b into c, can I say the time complexity is going to be order of b? Right? As simple as that. And if I talk about the space complexity, now you can think that I'm not creating any array or any vector or any data structure inside the function. So inside one function call, there is no extra space getting used. But this call stack is present in the memory only, right? When you actually go for a raised per b, then a raised per b minus 1, a raised per b minus 2, and so on, this actually consumes memory, right? This actually consumes memory. If I would have implemented it iteratively, there were no stack frames. There was only one stack frame to calculate a raised per b, and there would have been a for loop. There would not have been any such more stack frames. So now you can see that because it is a recursive function, with the increase in the value of b, the number of stack frames are also going to increase. And in each stack frame, you are consuming some space. So in each stack frame, if you are consuming constant space and there are b such stack frames, can I say the space complexity is also going to be order of b? And time complexity that we have seen is order of b. Can I say that? So this is how you can calculate the time and space complexity of recursive functions, at least in your initial part. That you have to just check that how many stack frames at any point of time were there in the call stack. That is the maximum number of stack frames. And in each stack frame, how much space you are consuming. You can just multiply the number of stack frames with the space in each stack frame and you will get space complexity. Then time can be calculated as total number of function calls that happened multiplied by the number of operations in each function call, right? This is how you can calculate the time and space complexity of recursive functions. That means if I go and try to calculate the time complexity of factorial, now just think about it. In one function call, there is a if check, there is a multiplication, and there is a function call. So there is constant time operation in one function call. And how many function calls are there? From n, you go to n minus 1. From n minus 1, you n minus 2, n minus 3, n minus 4, so on and so forth. You go till 1. So from n to 1, you make n function calls, right? So technically, from n, you go to n minus 1, n minus 2, n minus 3, so on, up till 1. So how many function calls are there? There are n function calls. In each function call, you are doing order of one task. So the time complexity is going to be order of n. And the space complexity will also be order of n, because at some point of time in the whole stack frame, in the whole call stack, all of these stack frames must be present. And in each stack frame, you are using just constant space. So the space complexity also becomes order of n. So this is how you can compute the time and space complexity of recursive functions. So throughout the whole, I would say, module, whatever recursive functions we are going to write, we are going to try to figure out that somehow we can calculate the time and space complexity for it. I'm going to show you different techniques to calculate time and space complexity for different recursive functions, but at least for the starting point, this should be a good to go. Now, because the basic power function is order of b, if I want to improve the efficiency, what can we do? Now, of course, 2 raised to the power 8 can be written as 2 into 2 raised to the power 7. Of course, this is a valid statement to give. But there is one more way in which we can represent 2 raised to the power 8. 2 raised to the power 8 can be represented as 2 raised to the power 4 into 2 raised to the power 4. Can I say that? Right? Similarly, if you have, let's say, 2 raised to the power 9, then 2 raised to the power 9 can be written as 2 into 2 raised to the power 4 into 2 raised to the power 4. Right? And what is happening here? What is actually happening here? If let's say I have a value a raised to the power b, then if b is even, then I can represent a raised to the power b as a raised to the power b by 2 into a raised to the power b by 2. For example, this 2 raised to the power 8 is what? 8 by 2 into 8 by 2. Or if b is odd, then we can represent it as a into a raised to the power b by 2 into a raised to the power b by 2. Think about it. What is 9 by 2? 9 by 2 in C++ is 4, right? Or Java also it is 4. So if you do 9 by 2, 9 by 2, this will only become 2 raised to the power 8. Because it is odd, you need to multiply an extra 2. Right? So if b is odd, you can use this. If b is even, you can use this. Can I say that? This can also be a way of segregating our logic, right? So if I write a function f of a comma b that returns a raised to the power b, can I say that if b is even, I can compute it like this. And if b is odd, I can compute it like this. Right? So Now if you see the recurrence, you have a function f of a comma b that you want to implement recursively. So if somehow you can assume that f of a comma b by 2 works correctly, if you assume f of a comma b by 2 works correctly, then you can call for f of a comma b by 2, f of a comma b by 2, and then you can compute f of a comma b, right? As simple as that. And again, the base case remains same. If b is 0, the answer is going to be 1. The base case still remains same. No change at all in the base case. But do you think if I write the recursive implementation like this, like, don't worry how I'm going to handle if cases and everything, don't worry, I'll implement this. But do you think this is still efficient? So what I'm trying to convey here is that although I have written the reduction factor as 2, like from earlier from b we were going to b minus 1, now we are going to b by 2, b by 2. It looks like b by 2 will make the algorithm more efficient, but it is technically not. For example, if you want to calculate 2 raised to the power 4, right? So if you calculate 2 raised to the power 4, it is going to ask you for 2 raised to the power 2, 2 raised to the power 2, or let's start with this 2 raised to the power 8. Let's start with even bigger value. Let's start with 2 raised to the power 8. It is going to expect you to calculate 2 raised to the power 4, 2 raised to the power 4, right? Then you are going to calculate 2 raised to the power 2, 2 raised to the power 2, 2 raised to the power 2, 2 raised to the power 2. Then you are going to calculate 2 raised to the power 1, 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 all over. And at last, everything is going to call to the base case, right? 2 raised to the power 0, 2 raised to the power 0. All of these are 2 raised to the power 0. 2 raised to the power 0. If you see technically, we are doing a lot of function calls here. Because earlier, if somebody asked me to do 2 raised to the power 8, what did I used to do? I used to go and calculate 2 raised to the power 7, 2 raised to the power 6, 2 raised to the power 5, 2 raised to the power 4, 2 raised to the power 3, 2 raised to the power 2, 2 raised to the power 1, 2 raised to the power 0. This was the earlier course of execution. This time the course of execution looks with the reduction factor of 2, but the number of function calls has like a significant increase. If you see, here we have 2 raised to the power 0 function calls. Here we have 2 raised to the power 1 function calls. Here we have 2 raised to the power 2 function calls. Here we have 2 raised to the power 3 function calls. Here we have 2 raised to the power 4 function calls. Can I say that? Can I say that? So if you sum them up, this will be, let's say if you want to calculate a raised to the power b, then on the 0th level you will be having 2 raised to the power 0 function calls. For example, a raised to the power b you have to calculate, you will go to a2 b by 2, a raised to the power b by 2, then you will go for a raised to the power b by 4, a raised to the power b by 4, and so on. So on the first level there will be 2 raised to the power 0 function calls, then there will be 2 raised to the power 1 function calls, then there will be 2 raised to the power 2 function calls, and so on and so on, right? Can I say at last how many function calls are there? You can see even if you avoid the base cases, still you have 2 raised to the power 3 function calls, right? So can I say 2 raised to the power 3 is what? 2 raised to the power log of b to the base 2. Can I say that? 2 raised to the power 3 can be written as 2 raised to the power log of b to the base 2. See, what is b? 8. What is log of a to the base 2? Log of a to the base 2 is 3, right? So this is going to be what? 2 raised to the power log of b to the base 2 plus 1. So can I say the final term is going to be 2 raised to the power log of b to the base 2 plus 1. Let's take another example. If let's say somebody asks you for 3 raised to the power 8, or let's 3 raised to the power 16. You are going to call for 3 raised to the power 8, 3 raised to the power 8. Then 3 raised to the power 4, 3 raised to the power 4, 3 raised to the power 4, 3 raised to the power 4. Then again 3 raised to the power 2. Same thing here, 3 raised to the power 2. Then technically 3 raised to the power 1. Then from everywhere 3 raised to the power 1. And then 3 raised to the power 0. everywhere 3 raised to the power 0 and so on. So if you see, here you have 2 raised power 0 function calls, 2 raised power 1 function calls, 2 raised power 2 function calls. Here you will be having 2 raised power 3 function calls. Here you will be having 2 raised power 4 function calls. Here you will be having 2 raised power 5 function calls. If you see the second last level, can I say you have 2 raised to the power log of 16 to the base 2 function calls? What is 16 to the base 2? 4. So on the last level, you have 2 raised to the power log of 16 to the base 2 plus 1 function calls, right? So these many function calls are there. On the 0th level, this many function calls. First level, this many function calls. Second level, this many function calls, and so on. What is the total number of function calls? This is a geometric progression, right? What is a geometric progression? Geometric progression is a series which is in the form of A, AR, AR square, AR cube, and so on. A raised to the power, AR raised to the power n minus 1. What is the sum of this series? Sum of this series is, if R is greater than 1, then A into R raised to the power n minus 1 upon R minus 1, where n is the total number of terms. See, from 0, 1, 2, 3, 4 till n minus 1 is n terms. Now, if I apply the same formula on our series, what is A? What is the first term? It is 2 raised power 0. 2 raised power 0 is 1 multiplied by R. What is the multiplicative factor? Every time the next expression is a multiplication of 2. Total number of terms. From 0 to log B plus 1 is log B to the base 2 plus 2 minus 1 upon 2 minus 1. See, from 0 to log B to the base 2 plus 1 is log B to the base 2 plus 2 terms. So we simplify it as 2 raised to the power log of B to the base 2 plus 2 minus 1. Now can I say if the value of B is extremely high, then log B to the base 2 plus 2 is log B only, and this minus 1 term can also be avoided. So can I say it is approximately equal to log B to the base 2? And what is A raised to the power log of B to the base A? This value is equals to B. So what is 2 raised to the power log of B to the base 2? It is equals to B. So can I say approximately total number, and it's a bit more than this only, but approximately the number of function calls are B only. And if you see, here also the number of function calls were B only. And in each function call, here also you will be doing constant time operation, because you just have to do if check and multiply. If check and multiply. So can I say, even if we have this relation, the time complexity is going to be order of B, right? The only factor that will reduce in this complexity is going to be the space. Because if you see, these things don't grow parallelly, right? From 2 raised to the power 8, you will first call 2 raised power 4, then you will call 2 raised power 2, then you will call 2 raised power 1, then you will call 2 raised power 0. Then you will come back and then again call 2 raised power 0, then you will come back, then you will come back and then call 2 raised power 1. So I'll show you that how these, I would say, recursive branches don't go parallelly. They are technically going to go linearly, right? They are going to linearly grow, right? They are not going to grow parallelly. So the space will be better than B. It will be around log B. I'll show you in some other problem. But my agenda was time here, to increase the time efficiency, and the time efficiency has not increased. With this relation, the time complexity has not improved. Why the time complexity has not improved? Because there is a small operation which is the culprit operation. There is one small thing that we are doing which is the whole culprit of the whole problem. And that's what we have to actually identify. So let me just help you with a quick revision of how I approach the complexity. I'm saying that 2 raised to the power 8 was earlier written as 2 into 2 raised to the power 7. I can write 2 raised to the power 8 as 2 raised to the power 4 into 2 raised to the power 4 also. That is, if we have to calculate a raised to the power b, I can calculate it using a raised to the power b by 2 into a raised to the power b by 2. And if it is odd, then I'll just multiply another a to it. So based on this, I wrote a recursive relation that if I want to calculate f of a comma b, and I assume that f of a comma b by 2 works correctly, then I can call f of a comma b by 2 multiplied by f of a comma b by 2. This will give me a raised to the power b by 2, a raised to the power b by 2, and multiply both of them. we will get a raised to the power b. As simple as that. Similar thing we just extended. Now it looks like that b reduces to b by 2, so the efficiency might have increased. But no, the efficiency is still not that good. Let me show you why. Because technically, 2 raised to the power 8 is going to call for 2 raised to the power 4, 2 raised to the power 4. 2 raised to the power 4 is going to call for 2 raised to the power 2, 2 raised to the power 2. Here also 2 raised to the power 2, 2 raised to the power 2. Every 2 raised to the power 2 is going to call for 2 raised to the power 1, 2 raised to the power 1. You can see. And then every 2 raised to the power 1 is going to call for 2 raised to the power 0, and so on. And what was the formula that we wrote? The formula that we wrote was number of function calls multiplied by number of instructions in each function call. So what is the total number of function calls? On this level, there is 2 raised to the power 0 function calls. On this level, there is 2 raised to the power 1 function calls. On this particular level, there are 2 raised to the power 2 function calls. On this particular level, there are 2 raised to the power 3 function calls, and so on. Right? So how many total function calls are there? Can I say the sum of all of these? And these looks like GP, right? These looks like GP. So I can say that the number of function calls are 2 raised to the power 0 plus 2 raised to the power 1 plus 2 raised to the power 2, so on and so forth. What is the last term? We have to figure out the last term. In order to figure out the last term, see the second last level. Can I say the second last level is what? 2 raised to the power log of b to the base 2, a to the base 2. Here also, second last level is 2 raised to the power log of b to the base 2. See, 2 raised to the power 4. So the last level is going to be what? 2 raised to the power log of b to the base 2 plus 1. Here also 2 raised to the power log of b to the base 2 plus 1 is 2 raised to the power 4. Right? So this is the last term that we have got. And this is a geometric progression. What is a geometric progression? A series which goes in terms like this: AR square, AR cube, so on and so forth, A raised to the power R, sorry, A into R raised to the power N minus 1. And R is greater than 1. So the sum of the GP becomes something like this, where A is the first term, R is the multiplicative factor, N is the total number of terms. Now, if I apply this same formula in our case, what is the first term? The first term is 2 raised to the power 0. So 2 raised to the power 0 is 1. Can I say that? 2 raised to the power 0 is 1. Then R raised to the power N. What is R? R is also 2. You can see every time the factor is multiplied with 2 only. See, 1 into 2 raised to the power 0, 1 into 2 raised to the power 1, 1 into 2 raised to the power 2. So every time it increases, right? So R is 2, you can see 2, 2. And what is the total number of terms? If 0 to n minus 1 gives you n, 0 to log b plus 1 will give you log b plus 2. Right? And this 2 minus 1 becomes 1. This 1 is multiplied, nothing much. We are left with this. In this case, if we avoid plus 2 and minus 1, because these are not going to affect the overall computation a lot if b is very big, then we will be left with 2 raised to the power log of b to the base 2. Can I say that? We'll be left with 2 raised to the power log of b to the base 2, right? If you can avoid this plus 2 and minus 1, because these are lower degree terms, you will be left with log of b to the base 2. So it will be total 2 raised to the power log of b to the base 2. Or what you can do is, you can write this 2 as log of 4 to the base 2. Then log b to the base 2 and log 4 to the base 2 will become log 4b to the base 2, right? And this term will become 2 raised to the power log of 4b to the base 2. Still 4 is a constant, so nothing will matter as such. That's why I just avoided the terms directly here only. So you have 2 raised to the power log of b to the base 2. We know that there is an identity for a greater than 0 and a is a constant. So a raised to the power log of b to the base a is equals to b. So can I say this term will become b? So the total number of function calls are b, or I would say approximately order of b. So if the total number of function calls are order of b, and in each function call you are just doing if check, so in each function call you are having constant time. So c into b is going to be order of b. And now we are going to see how we can optimize it. Now, if you want to improve this, the only statement that is causing this whole inefficiency is that once we have already computed f of a comma b by 2, that is a raised per b by 2 is already computed. I am again going and computing f of a comma b by 2. See, this part and this part are identical. I'm doing the same computations again. I'm repeating the computations. And the more deeper you go in the recursion, these computations increase. For example, this whole part and this whole part is same. This whole part and this whole part is same, right? So we are repeating the computations despite the fact that a comma b by 2, a comma b by 2, f of a comma b by 2 is already computed once. We don't need to compute it again. What we can say here is that f of a comma b can be written as, if b is even, then we can write it as f of a comma b by 2 whole square. And if b is odd, then we can write it as a into f of a comma b by 2 whole square. So what I'm going to do, I'm going to store the value of f of a comma b by 2 and then just square it. I'll just square it. That means if I have to calculate 2 raised to the power 8, I will just go and calculate 2 raised to the power 4. For calculating 2 raised to the power 4, I'll just calculate 2 raised to the power 2. Then I'll calculate 2 raised to the power 1, I'll calculate 2 raised to the power 0. When I'll come back, I'll square it. When I'll come back, I'll square it. When I'll come back, I'll square it. Right? So if you see, then on this level, there is only one function call. On this level, 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 one function call. How many total function calls you have? 1 plus 1 plus 1, so on and so forth, 1. How many times? Can you say that if this is the 0th level, first level, second level, so on, and let's say this is the kth level, and this is the kth level, right? Or you can see it in opposite terms also. 0, 1, 2, so on and so forth, k. Right? Can I say that this whole terminology reduces k to be approximately equal to log of b to the base 2? See? 8 is what? Like 1, 2, 3, 4. Approximately, there are 4 function calls. Can I say it is somehow in the order of log b? You might be thinking, sir, how it is order of log b? Let me show you. So, if let's say you want to compute 2 raised to the power 8, this is, let's say, the 0th level. Okay. You reduced it to 2 raised to the power 4. This is the first level. You reduce it to 2 raised to the power 2. This is the second level, and so on. So can I say from 2 raised to the power 8, you go to 2 raised to the power 4, you go to 2 raised to the power 2, you go to 2 raised to the power 1, you go to 2 raised to the power 0. Let's say there are total k terms. Right? There are total these terms. We need to calculate now that approximately how many terms are these. Let's say there are k terms. Now if you carefully see, from 8, that is, if I just focus on power, from 8 I am going to 4, from 4 to 2, 2 to 1, 1 to 0. And this 8 can be written as 2 raised to the power 3, 2 raised to the power 2, 2 raised to the power 1, 2 raised to the power 0, right? And then 0. Can I say that? If I just avoid this term of 0, and say that these are approximately k terms, because k minus 1 terms are also k terms, then 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, so on and so forth, 2 raised to the power k, because there were k terms, is equals to actually what? B. 2 raised to the power k is what? B. So if 2 raised to the power k is b approximately, then log of b to the base 2 is approximately equal to k. Can I say that? So we can say how many times this is getting called? Log b times. So the total number of function calls is what? Log of b to the base 2. And in each function call, you are going to do constant time operation because you have to just square the same value that you computed. Some if checks. So the time complexity is going to be order of log of b. As simple as that, right? And you can see the powers. If you just see from 1, you go to 2 raised power 1, 2 raised power 2, 2 raised power 3. At last, if you have at the kth level, the power is going to be approximately log of b to the base 2, right? That is, b is this power that is given to you, or the exponent. And using order of log of b, we have reduced the complexity of the algorithm, which was working in order of b, to order of log of b. That is the essence of this algorithm, right? Because we are not repeating anything, we are saving some calls. And that's how you can very efficiently implement power function. So in order to implement this, if I want to calculate f of a comma b, the base case remains same, right? That if b is 0, return 1. The base case remains same. And then we can say int value is equals to, just go and compute f of a comma b by 2. And we will store it. Just go and compute f of a comma b by 2. Then if b mod 2 is equals to 0, that is, if b is even, what will be the answer? The answer is going to be value into value. Else, if b is odd, the answer is going to be a into value into value. Can I say that? And now if you go and compute 2 raised to the power 8, you can see 2 raised power 8 is 256. If you go for 2 raised power 7, that is an odd number. That is 128. And you can see in one function call, you are doing constant operation only. See, if check, triggering a function call, right? Then again a if check, multiplication, else multiplication. That's it. So you are doing like 5 operations approximately. And there are log b such calls. So the time complexity of this algorithm is order of log b. The time complexity is going to be order of log b. And we don't care about the base, right? Because the bases can be interconverted inside log. So I hope this coding implementation is also making sense to everyone.